Hi everyone, this is Merrick Pua, the chemistry guru. Now in this video, we want to discuss the suggested solution for 2024 A-Levels H2 Chemistry Paper 1, question 21 to 30. So let's take a look at question 21. Compound Y, C7H7NO2 reacts with aqueous bromine at room temperature to produce C7H4NO2Br3. So what is the structural formula of Y? So we have four options here. Now, the topic tested in this question, it is linked to the electrophilic substitution of phenol or phenylamine. Because OH group, it is a highly activating group. NH2 group is also a highly activating group. So when attached to benzene, it will make benzene super reactive, and therefore benzene will undergo tri-substitution reaction. So if you look at the options A, B, C, D, you notice that your phenol is involved, phenylamine is involved, and what we can do to determine the extent of the reaction is just to simply compare the molecular formula. So if I take a look at the molecular formula for Y, C7H7NO2 versus the molecular formula for my product, C7H4NO2Br. So we can compare the molecular formula. What we are doing is we are losing 3 hydrogen. We're adding 3 bromine. So very nicely, this is consistent with the substitution reaction, electrophilic substitution of benzene, where the bromine comes in to my benzene and it replaces or it substitutes out a hydrogen. So this is therefore a tri-substitution reaction because of this highly activating group, either my OH group or NH2 group. So for each of these options, right, we just need to look out for the highly activating group and we see whether is there your substitution taking place and we want a tri-substitution. And if I look at option A, the highly activating group is this one, the phenol, and it is 2,4 directing, but you notice we can only have a di-substitution because position 4 is taken up by another group. So therefore, I can only sub 2 bromine. A will not be my answer because I need to sub 3 bromine. B, now the highly activating group is my NH2. Same as the previous case, I can only sub 2 bromine because position 4 is being blocked out by another group. So B is not my answer. C, it is the NH2, which is the highly activating group. And therefore, I will be able to sub the bromine to position 2, position 4, position 6. So all the slots are available. This guy can go up to tri-substitution, so therefore C is my answer. D, your NH2 group, it is the highly activating group. So it is again 2,4 directing, but it can only have 2 substitution because one of the position 2, is being blocked up by another group. So the answer to this question, where we can have 3 substitution involving bromine, will be C. Okay, next, how about question 22? Which reaction will form CH3 to CH, CH2, CO2H? So we have 4 reactions. A, 2-methyl-butane 1-ol with concentrated sulfuric acid. B, 3-methyl-butane 2-ol with acidified manganate. C, 2-methyl-propane nitrile with dilute sodium hydroxide. D, 3-methyl-butane 1-ol with acidified dichromate. So the topic tested in this question, of course, is under organic chem, but we have various functional group, some alcohols and nitrile. So it's targeting the organic reactions. So basically, are we familiar with the reactions involving your alcohol and your nitrile? The compound that we want to form, it is something like this. So what I've done is instead of using the structural formula, I try to draw out the displayed formula without the hydrogen bonded to my alkyl carbon because it is distracting. So the product that I'm expected to get, straight chain 4 carbon. Position 1, it is an acid group. Then position 3, there's a methyl group that is attached to it. So later when we do comparison, it is easier for us to compare as compared to looking at structural formula because the bonds, if you're using the structural formula, the bonds are not shown. So it is a little bit more abstract, harder for us to visualize. So let us run through the options. Involving A, 2-methyl-butane 1-ol, we should do something like this. Straight chain 4 carbon. Position 1, there's an OH group, 1-ol. Methyl group is on carbon position 2. Concentrated sulfuric acid, this is an elimination reaction. You're taking away water, take away OH from carbon 1, take away hydrogen from carbon 2, then you form a double bond between carbons number 1 and 2. This is the product. that we're going to get. Obviously, this is not the acid that we want, so A is not true. B, 3-methyl-butane-2-ol with acidified manganate, which is oxidation. So 3-methyl-butane-2-ol, OH group is on carbon position 2, methyl group is on carbon position 3. If I were to oxidize this guy, I will convert the secondary alcohol to a ketone. So I'll end up with a ketone, and it's also not my answer. I want to have an acid present. Involving C, 2-methyl-propane nitrile with dilute sodium hydroxide. Now, your propane nitrile is something like this, 3 carbon, then carbon number 1 is a triple bond N, this is my nitrile. 2-methyl means that there's a CH3 on carbon position 2, and involving NaOH aqueous, this would be hydrolysis, and my nitrile can be hydrolyzed to form conjugate base involving my acid. Acidic hydrolysis is going to form COOH, alkaline hydrolysis, it is going to form COO minus. So your compound, I have a straight chain 3 carbon, methyl group on carbon position 2, acid or salt of acid on carbon position 1. So it's still not what we want here. I want a straight chain 4 carbon, and methyl group on carbon position 3, then carbon 1, it is an acid group. So this guy, you notice, is a little bit short for because the number of carbon is not sufficient. C is not my answer. Finally, D, 3-methyl-butane-1-ol with acidified dichromate. So again, dichromate is an oxidizing agent. Primary alcohol, you can oxidize it to my acid group. Methyl group is on carbon position 3. I'm going to get this guy, straight chain 4 carbon. Carbon number 1 is acid. Carbon number 3, there's a methyl group. So this is a perfect match involving what we want to form in the product. So answer to this question will be D. Next, how about question 23? Now, 23, which statement is correct? A, ethanol has a bigger pKa value than phenol because the ethoxide ion is more stable than the phenoxide ion. Then B, ethanol has a smaller pKa value than water because of the donating effect of your ethyl group in the ethoxide ion. C, phenol has a bigger Ka value than water because lone pair of electrons on my oxygen atom is drawn into the delocalized electron ring system. Then D, phenol has a smaller Ka value than ethanol because it is a stronger acid than ethanol. So which of the statement is true? If you run through the options, we notice that we're just comparing acidity involving all these functional groups, ethanol versus phenol versus water. So the trend is here involving acidity for alcohol versus phenol versus water. So we actually know that phenol is more acidic than water. Water is more acidic than alcohol. Acid is more acidic than phenol. Acid is way on the left-hand side. Acid, it is the most acidic functional group that we have in syllabus. But this question, we're not talking about acids, so we can drop that. So acidity-wise and the strength-wise, phenol is more acidic than water. Water is more acidic than alcohol. So this one we know. And the Ka value and the pKa value are just values that we can use to measure acidity. So Ka, which is my acid dissociation constant, bigger Ka, you're more acidic. Smaller Ka will be less acidic. So phenol is more acidic. I'll have a bigger Ka value for phenol, smallest Ka for alcohol. pKa is just minus log Ka, so the trend will be opposite. And this will mean that for acidity, the stronger acid will have a smaller pKa value, the weaker acid will have a bigger pKa value. So we will expect comparing your pKa value, phenol should have the smallest pKa value, alcohol should have the biggest pKa value. So all this we want to establish. And once we have that, then in general, we are able to handle this question. Another thing that we want to recap is the concept that we will use to explain acidity. So acidity in organic chem, we will focus on stability of conjugate base. So the weak acid, whether you are an alcohol or phenol or acid, when it is a weak acid, it is partially dissociated. And this A- form, it is a conjugate base. So we will focus on the stability of the conjugate base. If the conjugate base is more stable, if let's say this A- is more stable, means that the system actually likes to form the more stable species, like to form A-, so you favor the forward reaction. Position of equilibrium will shift towards the right-hand side, favor the formation of my more stable conjugate base, and then as a consequence, I'm also going to release more H+, because H+ is the product. So this will mean that the weak acid is more acidic. So essentially, the more stable the conjugate base, then the more acidic that weak acid. And therefore, if I consider the strength, if phenol is more acidic than water, water is more acidic than alcohol, then what we will do is we will compare stability for each of these guys' conjugate bases, and then we try to focus on the stability and explain how come your phenoxide is more stable than what the to try to explain how come your phenoxide is more stable than hydroxide. Hydroxide is more stable than your ethoxide. So conjugate base for phenol is here. We have O minus next to benzene, directly bonded to benzene. So the lone pair involving oxygen can interact with benzene, delocalize pi system of benzene, and then this will mean that the negative charge will be drawn into benzene, and the conjugate base is going to be stabilized by resonance. The negative charge will be dispersed over the delocalized pi system. It is resonance stabilized. So if it is stabilized, that's good. Make this conjugate base more stable than hydroxide. Hydroxide is a benchmark because when you have an O minus bonded to hydrogen, hydrogen is not a donating group, hydrogen is not a withdrawing group. So this one is as if your O minus is just by itself. It is not attached to any donating withdrawing group. So the stability will just be the benchmark. This is like a benchmark. And then from there, we do comparison. If compared to OH minus, if there are any ways for me to help to disperse the negative charge on oxygen, that will be stabilizing and make it more stable than OH minus. Then conversely, if there are any things that is able to push electron to O minus, then there will be destabilizing and it will make it less stable than your OH minus. So this OH minus is the benchmark. And if it is attached to benzene, then negative charge is dispersed, stabilizing. Means that phenoxide conjugate base more stable than your hydroxide. So phenol is more acidic than water. Then comparing my alcohol, the conjugate base is alkoxide, our group is donating, and it is pushing electron to O minus. Now O minus is already negatively charged, so if it wants to be stable, it actually doesn't like donating groups. I'm already negatively charged, you still want to give me more electron or it make me even more negative, and usually we will say that you will intensify negative charge on oxygen, and that's destabilizing. So if it is destabilized, less stable than OH minus, then it will mean that alcohol is less acidic than water. So the trend and the explanation, we've talked about it. And then once we have that concept, we can run through the options and see which one it is the correct answer. So involving A, ethanol has a bigger pKa value than phenol. Actually, this first part is okay, and it's true, because ethanol is less acidic, so therefore it has a bigger pKa value. Because the ethoxide ion is more stable than phenoxide ion, and that part is not true. The conjugate base involving ethanol, the ethoxide ion, is actually less stable. So A, it is not true because of this part that we have highlighted. Involving B, your ethanol has a smaller pK value than water. Now this statement itself is already not true because it is a weaker acid and it should have a bigger pKa value, so B is wrong. C, phenol has a bigger Ka value than water, which is true. It is more acidic because lone pair of electron on oxygen drawn into the delocalized electron ring system, which is exactly what we have here, correct? So this will mean that, okay, C, it is my answer. This is the best answer here. D, involving phenol has a smaller P. D, involving phenol has a smaller Ka value than ethanol. This one is not true because phenol is more acidic. So therefore, it should have a bigger Ka value. So answer to this question will be C. Okay, next, how about question 24? Propanone reacts with lithium aluminum hydride, which is a strong reducing agent. So propene doesn't react with lithium aluminum hydride. So which statements are correct? Statement number one, propanone, your C double bond O bond has a permanent dipole, which allows the carbon atom to be attacked by a nucleophile. Number two, when propene undergoes addition reaction, it reacts with a nucleophile in the first step. Number two is wrong because alkene should take part in electrophilic addition reaction. So the first thing that reacts with my alkene should be an electrophile, is not a nucleophile. Number three, lithium aluminum hydride reduces propanone to propanoic acid. So which of these statements is true? Now, the reason why your lithium aluminum hydride can reduce but not alkene is because of the nature involving your hydride. Lithium aluminum hydride, the oxidation state involving hydrogen in hydride is a -1. So it is equivalent to a H minus. And it actually functions as a nucleophile, functions as an electron-rich species. So it will only react with things that are electron poor. So it works very well with carbon that is partial positive charge, things like carbonyl carbon, that means ketone, aldehyde. Also works very well with acids and derivatives. Lithium aluminum hydride can reduce acid, can reduce ester, can reduce amide. Because the acid carbon and acid derivatives carbon, they're all partial positive charge. So lithium aluminum hydride will work very well because the reaction is still between an electrophile and nucleophile. Something positive attracts something negatively charged. And this is also the reason why it is not able to react with alkene functional group, because alkene is counted as electron rich. Hydride is also electron rich. I negative, you also negative, we don't like each other, correct? So if I'm negatively charged or if I'm electron rich, then I'll only react with things that are positive. There's no reaction between two negative species, which again, I think is interesting. We want to take note of that, because if I consider lithium aluminum hydride, it is a very strong reducing agent. Alkene is pretty reactive, takes part in a lot of reactions, some of them at room temperature. But then these two guys are that is reactive. You put them together, then nothing will happen between them, because both of them are electron rich. They have the same nature, so they are considered nucleophiles. So they're considered as nucleophiles. We do not expect reaction between two nucleophiles, two negative species. Okay. So once we understand what is going on here, let us run through the options. Number one, propanone. The C double bond O bond has a permanent dipole, which allows the carbon to be attacked by a nucleophile. So this one is true, because CO bond is polar, oxygen is a minus, carbon is a plus. And because if the carbon is positively charged or partial positive charge, it can be reacted by a nucleophile. In this case, my hydride. So statement number one is true. Number two is wrong. We've mentioned that alkene takes part in electrophilic addition reaction. First thing that goes in should be an electrophile. It's not a nucleophile. So number two is wrong. Number three, lithium aluminum hydride reduces your propanone to propanoic acid. Of course, this is not true. If you consider propanone versus propanoic acid, the functional group is actually on a different carbon. A propanone, the C double bond O is on carbon position 2. Your acid, the functional group is on carbon position 1. All right, so maybe if I were to scribble this in, propanone is something like this. Propanoic acid is something like this. So the reactive carbon is totally different. This one is reactive carbon is the second carbon. This reactive carbon is the first carbon. So there's no such reaction. You can one shot do this. If I want to do this, we will need to do this in a series of steps. I cannot do this in one step, and definitely not by reduction. And also, your reduction of your ketone should give me an alcohol. In this case, ketone should be reduced to propane 2-ol. It doesn't get reduced to acid. So it doesn't make sense here. Correct? So number 3 is not true. Only statement number 1 is true. So therefore, B is our answer. Okay, next, how about question 25? Dimethyl formamide is a colorless liquid that is hydrolyzed by aqueous sodium hydroxide. So the formula is given here. So what are the products of this hydrolysis reaction? Fairly straightforward, because if you look at this dimethyl formamide, you look at the functional group, I have an amide functional group. So we're just targeting the hydrolysis for our amide here. And we look at the compound. When you try to hydrolyze the amide, what we will do is we will break the amide bond. Amide bond is this one, right? The bond between carbon and nitrogen. So since we're doing alkaline hydrolysis, this portion involving the nitrogen will form amine. So CH3, CH3, nitrogen, and a hydrogen form my amine. Then the blue carbon in alkaline hydrolysis will be converted to salt of your acid. So HCO minus, Na plus. So this should be the product involving alkaline hydrolysis. And therefore, answer to this question, if you run through the options, the one where we have an amine and a salt of my acid will be option D. So D will be our answer. All right, next, how about question 26? A sample of H2NCH2COH. So this is my amino acid dissolved in water. pH of the solution is increased by adding an excess of hydroxide ions. So what type of organic species increases in concentration as a result? So is it anion, cation molecules with the ion? So we want to run this through. The topic tested in this question under amino acids, fairly straightforward. We have an amino acid. Amino acid just means that I have a compound, there's an acid group, and there's an amine group. So I have an acid that's acidic, obviously. I have an amine, which is a base. And when you try to throw in OH minus, excess OH minus, the acid will respond by reacting with the OH minus. So COH will become CO minus. Your amine, which is a base, so it doesn't respond to OH minus, the amine will just remain as NH2. What we are doing is when you're adding excess OH minus, you're just forming more and more of this guy, which is a negative species. I will form my anion. So the type of organic species that will increase in concentration will be a anion. So A will be our answer here. Next, how about question 27? Copper plating is one application of electrolysis. A current of 5.00 ampere passed through copper sulfate aqueous for 20 minutes. What is the maximum mass of copper that could be produced at the cathode. So the topic tested in this question is under electrochemistry, of course, focusing on electrolysis. So some calculation involved. Now at the cathode, it is a reduction. So the process is here, copper 2 plus 2 electron to copper. So copper metal will be deposited on the cathode. And we can use our Faraday's equation. My Q equals to IT. Charge equals to current times time. Current is in ampere. Time is in seconds. So 20 minutes, we need to convert it to seconds. So 5 times 20 minutes multiplied by 60 seconds. So this will give me 6,000 coulomb. This is the quantity of charge that is involved in the process. The next thing is we will use the other Faraday's equation. Q equals to number of mole of electron times Faraday's constant. I can find the number of mole of electron, right? The mole of electron is Q divided by F. Charge, we already have settled earlier, 6,000. Faraday's constant is the charge of 1 mole of electron. You can find this inside data booklet 96500. Mole of electron works out to be 0.06 Once you have this, then I can compare mole ratio. Can compare mole ratio, can find the number of mole of copper involved. So mole ratio of copper to electron is 1:2. So the number of mole of copper will be half times this value, which will be 0.03109. So once we have the mole of copper, we can find the mass, very simple, multiply by the atomic mass involving copper, 63.5. So mass of copper that we were expected to get is 1.97 gram. So maximum mass of copper will be C, 1.97 gram. Next, 28. A student noted the relevant standard electrode potentials and correctly deduced that bubbling O2 gas through an acidic solution of HBr aqueous should oxidize it to Br2 aqueous. So the reaction is supposed to be feasible. Later we're going to talk about it. So on bubbling air through an acidic solution of HBr aqueous in a test tube, nothing happened. Observe no effect. So why is that the case? So possibility number 1, oxygen pressure smaller than 1 atmosphere. Number 2, activation energy for the reaction is high. Number 3, Br minus concentration much larger than 1 mole per dm cube. So again, we have to decide whether the statement makes sense. Is it true or not true? Or is it reasonable or not? Then the next thing is, so what if it is true? If it is true, then does it mean that the reaction that is supposed to be feasible turns out to be not feasible? So there are 2 layers to that. We have to consider this part by part. So the topic tested is under electrochem, targeting feasibility, predicting feasibility. So the actual half equations that we should be using inside the data booklet, since the question tells us that the student noted that the relevant standard electrode potential, so we should also be able to find these 2 half equations involving Br minus oxidized to Br2. E value inside data booklet is plus 1.07 volt. And then oxygen is reduced to water. We should be choosing O2 on the left-hand side of the half equation because it undergoes reduction. And we should also be using the half equation involving H plus because question mentioned that it is in acidic medium. So the half equation that we should be using is O2 plus 4H plus 4 electron to give me 2 water. E value is 1.23 volt. So we only have O2 present and Br minus present. So Br minus oxidized, O2 reduced. I can calculate the E cell for this redox reaction. Reduction of O2 versus oxidation of bromine. E cell is reduction minus oxidation. 1.23 volt reduction of O2 minus the oxidation of my bromine plus 1.07. I end up with a positive value plus 0.16 volt. So we have the same conclusion as the student mentioned in the question. The reaction should be feasible. If it is in acidic medium, under standard condition. Standard condition means what? Temperature is 208 K, then concentration is 1 mole per dm cube, and pressure for gases will be at 1 atmosphere. Because the question does talk about the pressure and then the concentration, which is that non-standard condition. So later we want to link it to that. So statement number 1, is it valid? Does it make sense? If the oxygen pressure is smaller than 1 atmosphere, which is true, because the atmospheric pressure is for air. The 1 atmosphere is for air. And inside air, there are a lot of things, right? There are a lot of different gases, nitrogen, carbon dioxide, and so on. And oxygen is just one component of it, maybe about 20%. So the partial pressure for O2 is definitely much smaller than 1 atmosphere. It's not. 1 atmosphere is actually way smaller than that. So how would that lower partial pressure affect the position of equilibrium, affect the E value, and therefore affect the E cell and the feasibility of the process? So we will have to look back at the reduction half equation. And when there's a decrease in the partial pressure for my O2, you notice that O2, it is the reactant. So O2 partial pressure comes down. Then according to the Charteris principle, I'm going to favor the reverse reaction. POE will shift towards the left-hand side. When POE shifts towards the left-hand side, then the E value will drop. Remember E value, the standard electrode potential that you can find in the data booklet. Actually, it just measures the tendency for the fall reaction. It literally measures the tendency for the fall reaction, measures the tendency for reduction. Some of us will learn this as standard reduction potential, standard electrode potential. They mean the same thing now because they are describing the same process. So if the fall reaction is favored, means that reduction is favored, E value will go up. If the reverse reaction is favored, that means you are not favoring or you are disfavoring reduction, then the E value is going to come down. So if I favor the reverse reaction, E value goes down. It's no longer 1.23. It will be a smaller value or less positive value than 1.23. And if you try to calculate E cell, which is E reduction minus E oxidation, when you have a smaller E reduction or less positive E reduction, then your E cell will also be less positive, which is bad, huh? Because less positive means less visible. So it's quite easy to become negative because the E cell calculated is only 0.16 volt. You decrease the E reduction to a small extent, quite a small extent, then it's very easy for the E cell to be negative and then the reaction is no longer feasible. So number one is okay because this is true. The oxygen pressure is smaller than 1 atmosphere, it is true. And the fact that if it is smaller than 1 atmosphere, it will actually cause the E reduction to come down, and therefore the E cell to be less positive and make the reaction less feasible. That's why we end up not observing the reaction. So statement number one definitely can be part of the explanation. Next one, how about number two? Number two, the activation energy for the reaction is high. Now, if this were true, then your reaction would be kinetically not feasible. Now, remember feasibility, there are two different aspects. One type is thermodynamic feasibility, which talks about the likelihood of a process taking place. We measure or we calculate this or deduce thermodynamic feasibility using a few terms in syllabus: Gibbs free energy, delta G, E cell under electrochem, and equilibrium constant K. So all these three terms, they're actually measuring the same type of feasibility, thermodynamic feasibility. So thermodynamic feasibility, we can calculate, we can predict, we can decide whether this one feasible or not feasible. Kinetic feasibility is a little bit more fuzzy. Kinetic feasibility says that it is based on the rate of the reaction. So the higher the activation energy, then the harder the reaction to proceed. So if the activation energy is too high, then the rate of the reaction is so slow that we actually don't really observe it. It is kinetically not feasible. The issue with kinetic feasibility is we can't really predict whether this is true or not. So that's a possibility. That's why I put a question mark here. If it is true, then if the activation energy is high, really is high, then the reaction will be kinetically not feasible because the rate of the reaction is too slow. The rate of the reaction is too slow for us to observe. But based on the information given in the question, we are not able to tell for sure whether the activation energy is it truly high or not. So it is like a question mark. We can consider this to be an option, but then we see what are the permutations given in my options A, B, C, D. How about number three? Number three, the Br minus concentration is much larger than 1 mole per dm cube. Possible, that is the case. But so what if it is true? How does it affect the E value? And in turn, how does it affect the E cell? So we have to try to deduce that. So if my Br minus concentration goes up, and Br minus, it is the product concentration increases, then it's going to favor the reverse reaction. Same idea as we've discussed previously for part one. If I favor the reverse reaction, means that the E value will drop. So E value measures the tendency for the fall reaction. Favor the fall reaction, E value goes up. Favor the reverse reaction, E value will come down. It will not be 1.07 volt, it will be less positive than this. So this is E oxidation. And if I were to sub this decreasing E oxidation or less positive E oxidation into a E cell is equals to E reduction minus E oxidation. When E oxidation is a smaller value, your E cell will be a bigger value. So if this were true, then you actually mean that the reaction is more feasible. So we will expect the reaction to occur rather than it doesn't occur. So statement number three, if it is true, then we will expect the reaction to be more feasible. So it doesn't explain what the question mentioned. Actually, there's no reaction here. Number three is not part of the answer. So number one is definitely correct. Number two is maybe. Number three is definitely wrong. So which could be reasons for this? we will choose based on A, B, C, D. Statement number 1 must be true. Statement number 3 must be not true. Number 2 depends. You notice involving the only possibility where number 1 is correct, I only have A and B, because C don't have option number 1, D also don't have option number 1. Then we know that number 3 is definitely wrong. So A will be eliminated and B must be our answer, number 1 and number 2. So because of this, then we know that, okay, coming back to this statement, activation energy for the reaction is high. Yes, likely to be the case. If the activation energy is high, then rate of the reaction is very slow, so kinetically not feasible. So answer to this question will be B. Next, how about 29? 29, the 3D orbitals of the transition metal ions shown are split into two different energy levels in their octahedral complexes. So assume that the electrons occupy all the 3D orbitals singly before pairing up. So which row shows the number of electrons in the higher energy 3D orbitals when this splitting occurs? So we have a few options here involving manganese 2, iron 3, nickel 2, and copper 1. So the topic tested in this question, of course, is under transition metal, and it's targeting the DD orbital splitting involving octahedral complexes. So involving octahedral complexes given in the question, we need to know the splitting pattern is 2 on top, 3 at the bottom. So the 2 on top is my dx squared minus y squared orbital and dz squared orbital. So the reason why your x squared minus y squared and z squared orbital has a higher energy level when we form octahedral complexes. Octahedral complexes, the ligand comes in all perpendicular to each other in the x direction, y direction, z direction. They're all perpendicular to each other. So when the ligand comes in and approaches the metal center in all this direction, directly along the axis, then what they're going to do is they will interact or they will clash directly with the d orbitals that is also lying directly along the axis, which will be my dx squared minus y squared that is lying directly along the x and y axis, and my dz squared that is directly along my z axis. So these two orbitals will interact with my orbitals to a bigger extent if it is octahedral complex. So energy level will be pushed up to a greater extent. Then the other three guys, my dxy, dxz, and yz, interact with the ligand to a smaller extent. Energy level will be lower. So we need to know involving the splitting pattern for my d orbitals involving octahedral complexes is 2 on top and 3 at the bottom. Tetrahedral complexes is the other way around, 3 on top, 2 at the bottom. So we will focus on octahedral complexes here. 2, 3, 2 is on top, 3 is at the bottom. Next thing we're going to do is which row shows the number of electrons in the higher energy 3D orbitals. That means focusing on x squared minus y squared and z squared when this splitting occurs. Question also mentioned here that we're going to assume that the electrons will occupy all the d orbitals singly before pairing up. So we'll follow this rule. So this one given in the question. So involving A, Mn2 plus. Mn2 plus, the electronic configuration is here. It will be argon 3d5. So I have 5 electrons in my 3D subshell, and we will fill this up. Remember singly and with parallel spin. According to Hund's rule, question also mentioned that you will occupy all the orbitals singly first before we pair up. So the configuration 3d5 will be something like this. And I focus on the number of electron in the higher level, higher energy level. I have 2 electrons here. So A, I have 2 electrons in this higher energy 3D orbitals. Then we can do the same for the rest of them. Iron 3 plus is also 3d5, and therefore the number of electrons in the higher energy level is also 2. And then nickel 2 plus will be argon 3d8. 3d8, if you fill up, it will be something like this. Remember, we fill up your electrons singly and with parallel spin first. So first electron comes here, second electron is here, third electron is here, fourth and fifth electron. After that, when you try to put the remaining electrons, you start to pair up, number 6, number 7, number 8. So I have 2 electrons in the high energy level for nickel 2 plus. Finally, for copper plus is 3d10, which is fully filled. So I'll have 4 electrons in the higher energy level. And once we have worked out, then we can compare. I know that A is 2 electrons, B is 2 electrons, C is 2 electrons, D is 4 electrons in the higher energy level. So which one is valid? In this case, C will be my answer. Nickel 2 plus, number of electrons in the higher energy level is equals to 2. So answer to this question will be C. All right, final question for this exercise, question 30. An excess of SO2 is bubbled into warm solution containing VO2 plus ions in acidic condition. So what is the final oxidation state of vanadium? Now, the topic covered is under electrochemistry, targeting feasibility. And the idea is if I pull out all the relevant half equations from the data booklet, question mentioned that SO2 is bubbled into VO2 plus. So we can get the E value involving SO2. Inside the data booklet, there's only one value for sulfur dioxide, which is on the right side of the half equation. So SO2 will undergo oxidation to form sulfate, SO42 minus. E value is given here. And since SO2 is oxidized, and therefore it is reducing. And when we see VO2 plus, we will be able to find a half equation involving the reduction of this guy to VO plus 2 charge. E value is 1.00 volt. Then your VO plus 2 charge inside the data booklet, we also have this value. I can reduce it further to V3 plus, and V3 plus, I can reduce it to V2 plus, and V2 plus, I can even reduce it to metal. So all the E values are given here. What we want to do is, okay, when my SO2 is oxidized and you try to reduce my vanadium, so what is the extent that it can reduce my vanadium to? So is it only the first stage or the second stage, or is it able to reduce it all the way to metal? And therefore, for each of these reaction, we will calculate the E cell. If the reaction is feasible, then we will move on and proceed to the next stage. So we will keep on calculating E cell for each of the stages until we end up with a negative E cell. Then the reaction is not feasible, then the reaction officially will stop. So it's not difficult. So let's talk about it. So number one, you have SO2. SO2 always undergo oxidation. First one, can it reduce VO2 plus 1 charge to VO plus 2 charge? So it is the reaction between SO2 and VO2 plus charge. And E cell is reduction minus oxidation. 1 minus plus 0.17. It is a positive value because bigger number minus a smaller number. Positive value means that it is feasible. Then yes, I can form the VO2 plus charge. I do a bit of color coding so it's easier to reference. The yellow species can be formed. So once the yellow guy is formed, right, I have to consider, can it reduce the yellow guy to the blue guy? Can it reduce it to V3 plus? So I'm going to calculate the feasibility for that. The reaction for SO2 and the yellow species VO plus 2 charge, E cell is the EV reduction 0.34 minus E oxidation 0.17. So again, a bigger number minus a smaller number is going to be positive, and therefore the reaction is feasible. So yes, I will be able to form V3 plus. So V3 plus can be formed. So if I can form V3 plus, next thing we have to consider is, can it reduce even further? Can it form V2 plus? That means keep on calculating until you end up getting a negative E cell. So the reaction between SO2 and V3 plus, so the E cell is minus 0.26 minus a positive 0.17. So a negative number minus a positive number, it is going to be a negative number. So E cell is negative and the reaction is no longer feasible. So once the reaction is no longer feasible, then V2 plus is not formed. And if V2 plus is not formed, we don't need to consider, can it be reduced to metal? So the reaction already end off with V3 plus and it'll be stuck at V3 plus. So final oxidation state involving vanadium will be a +3. So answer to this question will be B.